Everybody on Zoom. That's interesting. Okay. Less than ideal. There's the attendance form. It's 7 o'clock. I guess we should start. Okay. Feel like there's something on. Oh, no class on Friday, right? No class on Friday. Don't come to class on Friday. I won't be here. Bless you. More blue pens. And no quiz this weekend either. No quiz. My when I was doing the class meeting corner, I was like, we're not gonna have class. We're only gonna have quizzes on days we have class on Friday. So if we don't have class on Friday, no quiz. So, no quiz. Enjoy your long weekend. Yeah. The other thing I'll point out is today is I guess the last day of class material before we start talking about trigonometry. So after today, the rest of the classes aside from the midterm, trigonometry. So we talk about radians and sine and cosine and tangent and all that good stuff. So that's coming up on Monday. But let's finish up talking about basically range. Like, yeah, there's some other stuff on this, but basically range we cover. So we've got inverses, more domain, and range. Last time we saw that if two functions are inverses, it is true that f of g of x and g of f of x are both the same, and they're both equal to x. So it's really, really important that they're not just equal to each other, they're also equal to x because they're undoing each other. So this right here is what we typically check to see if two functions are inverses. The other thing that is good to know, though, is that if two functions are inverses, their graphs will be reflections of each other in the line y equals x. So let's actually look at a couple examples here, or an example. Let's look at the function f of x equal to 2 to the x plus 1, which is a nice exponential function that's been shifted up by 1. So this function is going to have a y-intercept of 0, comma, by plugging 0, 2 to the 0 is 1, 1 plus 1 is 2. And it's going to have a horizontal asymptote shifted up by 1 of y equal to 1. Come on in, folks. We'll just start talking about inverse functions some more, and how to find and how they're going to be reflections of each other. So if I graph this one, here's my horizontal asymptote. I can plot a few points, but I don't really want to. I got the point 0, 2. I would get the point 1, 3, point 2, 5. Okay, fine. I'll plot some points. It'll look kind of like this. Great. The inverse function, well, in fact, we can even find the inverse function. So to find the inverse function, let's actually do that. So we're going to say for the inverse, we're going to write it as y equal to 2 to the x plus 1. And then we're going to switch x and y. So we're going to have x equal to 2 to the y plus 1. And then solving for y, we've got x minus 1 equal to 2 to the y. And although you could use a natural log here, I would use a log base 2 because that's kind of the most typical choice for the inverse function of a 2 to the something is using log. So keeping the bases the same is the more normal thing to do if you're trying to find an inverse function. So we're going to write this as log base 2 of x minus 1 is equal to y. Or I'm going to write g of x, although you could totally write f inverse of x. Yeah. G of x equal to log base 2 of x minus 1. So there's an inverse function, and let's talk about it before we graph it. So for g of x equal to log base 2 of x minus 1, instead of a horizontal asymptote at y equals 1, we're going to get a vertical asymptote at x equals 1. And instead of a y-intercept of 0, 2, well, if we set to find the x-intercept, if we set y equal to 0, 0 equals log base 2 of x minus 1, 2 to the 0 equals x minus 1, 1 equals x minus 1, so 1 plus 1 equals x. So instead of a y-intercept of 0, 2, we get an x-intercept of 2, 0. So we get that point, we get this vertical asymptote, and we get the usual logarithmic shape. And I really want to emphasize here, the x and y things are just interchanging, right? Instead of getting a horizontal asymptote of y equals 1, we get a vertical asymptote of x equals 1. Instead of this y-intercept of 0, 2, this x-intercept of 2, 0. We can also interchange other points, right? Instead of this point 1, 3, we're going to get the point 3, 1. Instead of the point 2, 5, we're going to get the point 5, 2. So there's really this literal interchange of the x's and the y's. And it's going to look like the usual logarithmic function. And then the whole point of this is that graphically, is that these look exactly like reflections of each other in the line y equals x. Which they are. So if you're trying to see what a function's inverse looks like, one thing we can do is just take the graph of it and reflect it across that line y equals x. Now, it's not super precise usually, but it will give you a good idea of how the inverse function looks. Okay. The other thing to note here is that for f inverse and f of x, their domain and their range switch, because the domain is just all the x things, the range is just all the y things. So if you're interchanging x and y, you're interchanging all the x things and all the y things. So what I want to say here is that the domain of f of x is the same as or is equal to the range of the inverse function, and vice versa. The range of f of x is equal to the domain of the inverse function, which we can totally see in this example. Right? In this example, our domain of f of x is, well, the domain of this function f of x is everything. There's no issues. All real numbers. And that is the same as the range of this red function g of x. And similarly, if I can fit this in here, the domain of the inverse function, which is, well, let's see, the domain, we don't quite get down to 1, but we start everything bigger than 1. So our domain there is everything from 1 to infinity. And that's the same as the range of the original function f of x. I really want you to take this to heart, right? The domain here is everything bigger than 1. The range here is everything bigger than 1. The range here is everything. The domain here is everything. So we really have this inverse relationship where the domain and the range. And the reason we're talking about this specifically today is because we're going to use the fact that the domain of the inverse function is the range of the original function. So if we're asked to find the range of the original function, one way to do it, which we saw last class, is to graph it and try and see what it looks like. But another way to do it, which is often what we're going to do, is to find the inverse function and then find the domain of the inverse function. The second method does have some drawbacks to it. One, not all functions have inverses. Two, sometimes you have to do some funky stuff to make it so it works. So there's never a perfect method for anything really, but this is a pretty good method for us. Yeah, so we can use this method to help us find the range when we don't want to graph it or we can't graph it. So sometimes graphing things, I mean, that's not true. You can usually graph things, but sometimes graphing is just very challenging. And even if we could graph it, it might still be hard to see what the range was. So that's what we're going to do today. We're going to find range by using the inverse function. But we're going to look at some more examples first. So just to kind of really drive home this fact that these inverse functions have interchanged everything, let's graph two more things. So both of these, f of x equal to 2x minus 4 over 3 and g of x equal to 3x plus 4 over 2 are inverse functions. Well, actually, we're not saying they're inverse functions. We're being asked to show they're inverse, right? So if I read the words here, it says show these are inverse functions. Typically, when someone asks you to show something's an inverse function, their expectation is for you to show the following. Oops. Their expectation is that you show that f of g of x is equal to x and that g of f of x is equal to x. I will say that over the years, I have certainly seen people show that two functions are inverse functions by starting with one of them and then finding the inverse function using the process we talked about last class and then getting to the other function. That is also perfectly fine. It's might not be what your teachers in the future expect you to do though. So just so you know, if someone asks you to show two functions are inverses, usually that means do this. Whereas if they ask you to find the inverse, that's where you start with one function, interchange things, and then do the work to find the other function. We're going to do it this way. So that doesn't mean you couldn't do it the other way on your own, perfectly fine. So let's show these are inverses. So I'm going to find f of g of x. Now we should be not surprised by the result here. F of 3x plus 4 over 2 is, well, let's see, f of x is 2x minus 4 over 3. So f of some stuff is 2 times my stuff minus 4 over 3. My stuff is the 3x plus 4 over 2. The 2's cancel. 2 divided by 2 is 1. And then I think it's worth rewriting. This is 3x plus 4 minus 4 over 3. The 4's cancel. 4 minus 4 is 0. And then finally we have 3x over 3, which is just equal to x. Just be a little careful here. I've definitely seen people in the past like say the 3's cancel here first, and while that's kind of works, technically when you're if you're canceling the 3's, you're dividing everything by 3. So if you were to do that, like if you were to go this way and say 3's cancel, then you should be left with kind of like a 4/3 minus 4/3. And then so just be careful about the order you cancel. And then the other direction, I want to find g of f of x, do g of 2x minus 4 over 3, which is going to be 3 times our stuff plus 4 over 2. So plug in the 2x minus 4. This might feel kind of like it's not necessary, right? Like, yeah, they're clearly inverses. This feels maybe a little tedious, but it is still work that needs to be done if someone asks you to show the functions are inverses. So then we divide 3 by 3 and get 1. We're left with 2x minus 4 plus 4 over 2. And then the 4's cancel. We've got 2x over 2. And then we've got x. So great. Whoops, sorry. Things check out. They are inverse functions. We have shown it. It is true. Now let's graph them. So something to be aware of with both these functions, they are both lines, even though they may be not written in the exact usual way. You might prefer to write f of x as 2/3 times x minus 4/3 instead of 2x minus 4 over 3. And you might prefer to write g of x as 3/2 x plus 4/2, which is just 2. Fine either way you want to write. If I'm graphing lines, I'm finding intercepts. So for f of x, I'm going to find my y-intercept by setting x equal to 0. If x is 0, f of 0 is going to be 2/3 times 0 minus 4/3 is minus 4/3. My x-intercept, so if I set the function equal to 0, it might be easier to write it the other way if I said equal to 0. So instead of writing as 2/3 x minus 4/3, I'm going to write it as 2x minus 4/3. So I'm going to set y equal to 0. So I'm going to write 2x minus 4 over 3 is equal to 0. Multiply both sides by 3. 2x minus 4 equals 0. 2x equals 4. X equals 2. So my y-intercept is 0, negative 4/3. My x-intercept is 2, 0. Plot those points, 2, 0. 0, negative 4/3 is not my favorite, but it's fine. So even though I talk about finding the y-intercepts, I'm going to also tell you if I want to make this graph look great. I'm probably going to try and pick a point in my mind that's extra just so I can make it so it's easier to get the points I want. Meaning, instead of plotting this point, even though I am going to plot it, there's my 0, -4/3. So you can kind of see that. What I'm also going to think of doing is picking a value of x like -1, because -1 times 2 is -2. -2 minus 4 is -6, and -6 divided by 3 is a nice integer -2. So if I plug in -1 for x, I get -2 for y. So I'm also thinking about making sure I go through that point there because it's kind of a more well-defined point. All right, then we graph it. Okay, so here's something that's nice to know. We know these functions are inverses, meaning all their x and y things should interchange. So I don't really need to go through the work of finding the x and y intercept for g of x because I already know them. For g of x, the y-intercept should be the same as the x-intercept for f of x. So my y-intercept should be, instead of 2, 0, 0, 2. And for g of x, my x-intercept, instead of being 0, -4/3, it should be -4/3, 0. It's kind of useful when it comes to graphing these things. So I'm going to also point out, instead of having the point -1, -2, I'm also going to have the point -2, -1 to make life a tiny bit easier. So at that point there, got that point there. I've got the intercept, which is right there about. And then we try our best to graph it. Sure, that'll look all right. Fun fact, if inverse functions cross each other, they have to cross each other on the line y = x. There's no other place where they can cross each other. That's the only place that they are ever the same. And so these definitely are reflections of each other in the line y = x. Cool. So really the point of this was just for you to see again that when you have inverse functions, they always have this graphical reality that they are reflections or mirror images of each other in the line y = x. It's a good thing to know. It comes up more often than you would actually think. Okay, but now we're done with the graphing. Like, fine, I don't want to graph anymore. We're going to move on to just saying, I'm going to find inverse. So I'm going to find domain and range without graphing. So let's look at the next question here. We're going to find the domain and range of f of x equal to x plus 3 over 3x minus 5 without graphing. Okay. Domain should be not too terrible. Domain is usually just look for the usual things. So for the domain, first of all, we're going to ask the usual 3 questions. Do I have division by 0 possibly? Oh, I do. There is division by 0. So we want to avoid that. So we're going to exclude where the denominator is equal to 0. In this case, that's going to end up being 3x equal to 5, x equal to 5/3. So our domain is going to be everything. Well, should I say, we should definitely check the other 2 things real quick. So are there any square roots? No. Are there any logarithms? No. So we've checked all the things. We only have this one thing to look at. So our domain here is everything but positive 5/3. So you can either do it this way and say we're missing that. We want everything else. You don't have to draw the number line. I like to. So my domain is everything from -infinity up to 5/3 exclusive. You don't want it. Union, everything from 5/3 exclusive to infinity. The domain is the relatively, comparatively easy part. The range is the part that's going to require more work. So to find the range, we first have to find the inverse function. So find f inverse of x. Really, I should say find the domain of f inverse of x. But to find the domain of the thing, you have to find the thing first. All right, so usual process for finding the inverse function, we're going to start with y equal to our function, x plus 3 over 3x minus 5, and we're going to interchange x and y. So x is equal to y plus 3 over 3y minus 5. And then we have to solve for y. And this is one of those situations where you're going to end up having to like multiply both sides by something and then get all the y's on one side and factor out a y. So if you see more than one y after you've interchanged things, you should prepare yourself to have to do a little more algebra, right? There's going to be more stuff where we have to make sure we get all the y's on one side. So I'm going to have x times 3y minus 5 equal to y plus 3 over 3y minus 5 times 3y minus 5. The whole point of multiplying both sides by 3y minus 5 is to cancel out that denominator because I don't want to deal with any denominators. And then let's see here. Distribute the x. So I have 3 or x times 3y, which is 3xy. X times minus 5 is minus 5x equals y plus 3. Okay, so just as a word of warning here, let me grab another piece of paper here. I never come prepared. I always have like all kinds of paper in other places and never write. So what I want to point out, I don't want to write on the same page just because I don't want it to be there. But the wrong thing to do here, or the not right thing to do, is to be like, oh, y equals 3xy minus 5x minus 3. That's not the right answer, right? Because our y has a y in it. So we definitely need to solve for y, but there can't be any y in that answer. Okay, so just make sure we're cool with that. So bring all the y things to one side. Doesn't matter which side you pick. I'm usually going to try and pick the side so that the other stuff ends up being positive. Meaning I could bring my y's to the right, but then the stuff that ends up on the left would be negative 3 minus 5x. So I'm going to make the other choice. So the stuff on the other side ends up being more positive. It doesn't really matter, but it's kind of a preference. So I'm going to bring my y's to the left side. I'm going to have 3xy minus y. Bring everything else to the right. So I'm going to have a positive 5x plus 3. Or if you preferred, you could have negative 5x minus 3 equal to y minus 3xy. Either way, totally fine. After we group all our y's on the same side, we factor out a y. We're left with a 3x minus 1 equal to 5x plus 3. And finally, solving for y, we get y equal to 5x plus 3 divided by 3x minus 1. And that is our inverse function. So f inverse of x is 5x plus 3 divided by 3x minus 1. And now we can answer the question that we were asked, which is, what is the range of our original function? So to find the range of f of x, we're going to find the domain of f inverse of x. And just like when we found the domain of f of x, we're just going to look for what we need to exclude. So in this case, we're again looking to exclude wherever the denominator is 0. So we're going to exclude where 3x minus 1 is equal to 0. Which if we solve, we get 3x equal to 1, we get x equal to 1/3. So we want everything but 1/3. So our range of f of x is going to be negative infinity to 1/3 exclusive union 1/3 exclusive to infinity. Everything except for 1/3. So that's the general process for finding the range of a function, not graphically. Find the inverse, find the domain. Are there any questions you want to ask before I think of anything I want to say? It's notable here that this original function, x plus 3 over 5, 3x minus 5, has a vertical asymptote at 5/3 and a horizontal asymptote at 1/3. And in this inverse function, we have the opposite things. This inverse function has a vertical asymptote at 1/3 and a horizontal asymptote at 5/3, which is typical because again, I know I've said it like 100 times, but when you have inverse functions, all the x and the y things interchange places. So any vertical asymptote becomes a horizontal asymptote and vice versa. Any vertical asymptote becomes horizontal asymptote. Kind of cool. Kind of neat, actually. I mean, it is really an interesting thing that you're like, oh, we're really just finding the inverse by literally switching x and y, which changes the input-output relationship. It might not seem that neat, but it is kind of neat. Okay. So sometimes no, actually not yet. Not yet. Sometimes, but not yet. This next one should be not as terrible. Can we see? Sure. So I would point out that although we're going to do this one maybe the long way, you could totally find the domain range of this function graphically. We've talked about logarithms enough to be able to know that their range is usually just everything. So we're gonna do it both ways to see it, but I will point out that for the domain here, we're just setting x plus 3 to be strictly greater than 0, which means we're going to get x to be strictly greater than -3. So our domain is going to be everything on which side of -3? The right or the left? The right side. So our domain is going to be everything from -3 all the way to infinity. That is our domain. Which if we think about the graph, right, you're just taking your usual logarithm graph and shifting it 3 to the left. So yeah, we're getting almost a -3, but not quite, and then everything to the right. If you haven't done the other kind of reflections or shifts or anything. The range here. So for a moment, if we think about the graph, if we just think of the graph, we're going to do it the other way too. If we think of the graph, we're like, oh, the range should be everything. Right? The logarithm goes way down to -infinity at the vertical asymptote. And then even though it does it really slowly, it does keep going up and up and up and up and up and up and up. Right? There is no upper limit to how high it gets. So the range really is everything. Well, let's talk about how we would do this a more analytical way, where we actually kind of do the work. So if we do the work, well, we're going to find the inverse function. We're going to find f inverse of x. So I'm going to take, I didn't write down, I guess I need to, yeah. So I'm going to write down y equal to log base 3 of x plus 3 and rewrite it as, or I should say not rewrite it, interchange. X equal to log base 3 of y plus 3. And then we try to solve for y. So I'm going to rewrite this as an exponential equation. My base is 3, my power is x, and it's equal to y plus 3. So then I'm going to solve for y, and I'm going to get y equal to 3 to the x minus 3. And so then if I write my inverse function, I have f inverse of x equal to 3 to the x minus 3. Okay, so if I want to find the domain specifically of f inverse, do we have any division by 0 possibilities? No. Do I have any even roots? Definitely not. Do I have any logarithms? For sure, no. You might kind of be like, well, James is kind of a logarithm. You go, well, no, there's not, right? I know we got this by taking the inverse of a logarithm, but our final result here has no logarithms, no roots, no fractions, there's no domain issues. So the domain here really is everything. You can plug in any value for x and get out some number. I will also point out, so, well, let me see. So, right, that jives with what we're saying here. I will also just mention, just for completeness sake, the range of this inverse function, right? If you think about this exponential function that's been shifted down by 3, it would have a horizontal asymptote at y equals -3, and this range would go almost all the way down to -3. So the range would certainly be -3 to infinity, but exclusive of -3. So really, again, just showcasing the fact that the domain and range of these inverse functions just interchange. Domain of f is the range of f inverse. The range of f is the domain of f inverse. Totally true. As long as there's no weirdness about your function being less than precisely perfectly equal, which I know it's not something we've really talked about, and it's not something we usually typically talk about, except in these next examples. Okay. Questions about this one? Oh yeah, lots of time. We only have a couple of examples left. So let's actually, I want to skip this next example first and go to the last page. The last page is a little bit weird, I feel like. But I want to do this one this way just to talk about it. So we're looking at We can see that. We're looking at the function f of x equal to 20 over x squared plus 4, and we are given that x is greater than or equal to 0. Now, why are we given this? Well, the reason we're given this is because if x weren't greater than or equal to 0, the function that we would have wouldn't actually be invertible. Here's what I mean. If I write down the function y equal to 20 over x squared plus 4, and I start graphing it, so I'm gonna just plot a couple points. So if I plug in x equal to 0, I get 20 over 4, which is 5. If I plug in x equal to 1, I get 20 over 5, which is 4. If I plug in x equal to 2, I get 20 over 8, which is, I don't know, 10 over 4, which is 5 over 2. Like there-ish. And if I plug in x equal, let's go one more. If I plug in x equal to 3, 20 over 13 is okay. That's not a very good choice, but whatever. Let's plug in x equal to 4. 20 over 18 is about 1. It's a little bigger than 1. So here's what I want you to see on this side. As x gets larger and larger and larger, what's going to happen to the y values? They get bigger, get smaller. Smaller, closer and closer and closer to 0, but never actually quite to 0, right? This will never equal 0 no matter how big x is, but it will get very, very close to it. This will definitely have a horizontal asymptote at y equals 0. And it looks kind of like this. Okay, but now if I started plugging in negative x values, I would get the same shape on the left. This graph is totally an even function. If you replace x with negative x, it still looks the same. And so if we were to graph the other side, it would do the same sort of thing. Like that. And the problem is that this function, if you have both sides of it, is not actually an invertible function. Because here's what happens. When you switch x and y, you really just reflect the whole function across the line y equals x. Well, if I take this function, and we're going to do it actually for real in a second. Well, in fact, let me just, I wish this was transparent so I could be like, boom, there it is. You can kind of see it. If you flip that function over the line y equals x, it kind of looks like that. We'll do it for real in a second here. But notably, that's not a function if you have both the blue part and the red part, because it fails the vertical line test. So that's why we're cutting off the red part, so that the part that we actually do end up flipping over is a function and passes the vertical line test. So when you talk about finding the domain, or I should say the range of a function, and you see that you've kind of limited the domain here at the beginning, it's because the person writing the question knows that the actual whole function is not invertible. And so they're just giving you the pieces that are going to be invertible. I want to show you though on Desmos, because I think it's kind of neat, the stuff you guys can do with this. So let me just grab this here real quick, just so I can show you. So we can totally graph the original function, y equal to, what was it? 20 over x squared plus 4. Cool, looks great. And then it's really easy to invert functions using Desmos without actually finding the inverse by literally just switching x and y. So you can totally graph x equal to 20 over y squared plus 4. And you totally get the inverse relationship. Again, not a function, right? This is totally not a function. But if you take this original function and limit the x's to be greater than or equal to 0, then you only get the right half. And if you do the same sort of restriction, but it's not the same exact restriction, because instead of saying x is greater than or equal to 0, we are switching x and y. So now for this other function, we have to say that it's going to be where y is greater than or equal to 0. Which gives you just that top piece, which is totally a function because it passes the vertical line test. So that's kind of what's going on here very, very specifically with this example. That's why we have said that we don't want, or that we only want when x is bigger than or equal to 0. Okay, so that's how we're going to talk about finding the domain range. Now, how do we do this? Well, graphing this or graphing the inverse is not something I'm very good at. I mean, I guess you can use Desmos to find it. You could totally kind of take this and say, well, James, I'm going to say what you said before and kind of just flip things. So instead of getting the 0.05, I'm going to get the 5, 0. And then instead of getting this stuff here, I'm going to get like this here. So we could maybe kind of think about this in a smart way and say, oh, well, the range is the range of this. I mean, you also could probably look at this function and be like, well, look, James, you're going as high as 5 and as low as almost 0. So the range of this is everything from 0 to 5, which is the same as the domain of this, right? The domain here is everything from 0 to 5. But let's pretend like we couldn't graph it. Someone said, you're not allowed to graph it. You must do it the hard way. And sometimes the reason really I'm mentioning this is because there are people who are going to show you this in a different way in the future and be like, yeah, they want you to do this weird thing. So here's how you deal with this if you're just dealing with the non-graphing method. So I'm going to start with y equal to 20 over x squared plus 4. And I'm going to remind myself, oh yeah, x is better be greater than or equal to 0. Sorry. Notes everywhere. One second. Let me make sure I'm not doing anything stupid here. Okay, yeah. So for the range, we're going to invert x and y. So x is equal to 20 over y squared plus 4. And then you can try and solve for y, but we should remember that since we interchange x and y, we better have y greater than or equal to 0. So now things get kind of weird. We're going to try and solve for y. It's going to be a little bit strange though. So if we multiply both sides by y squared plus 4, we get y squared plus 4 times x equal to 20. And then if we try and solve for y, I'm going to divide both sides by x. Y squared plus 4 equals 20 divided by x. That seems dangerous. And then y squared equals 20 divided by x minus 4. And then I'm going to get y equal to, now check this out. Normally, if we were square rooting both sides, we would say y equal to plus or minus the square root of 20 over x minus 4. But we know, since y has to be positive, we can't get the negative part here. So it's got to be just the positive part. Then we get y equal to the positive square root of 20 over x minus 4. So then your job is to find the domain of that, which seems like a lot more, right? Doesn't it seem like a terrible way to do this? You guys can say, yes, it is. This is definitely a problem where even though you can do it this way, and I feel like I kind of have to show you this, graphing it and thinking about what the graph looks like is a much more normal way of doing it. I'm going to talk, yeah, we got time. I'm going to talk about one more way to actually do this without kind of doing either thing. So, how many of you are going to the 17 series? Well, okay. This particular idea that we're going to talk about last year is really kind of how I would encourage all of you to see it, but it's kind of really takes hold in the 17 series when we talk about this stuff. So but doing this, so I want 20 over x minus 4 to be greater than or equal to 0. It's inside the square root. Also, I should point out that x has to be not equal to 0, because if x was 0, we'd be dividing by 0. All right. A word of warning here. We definitely do not want to solve this by doing the following. Grab that piece of paper again. So here's how we don't solve this. We don't do this. Add 4 to both sides, and then multiply both sides by x. Why don't we do that? Well, what if x was negative? Then when you multiply both sides by a negative, don't you have to change the direction of the inequality? That's why we don't do this, because you end up maybe losing some possible solutions or getting solutions where you shouldn't get solutions. So instead of doing that, we're going to keep everything on the same side and just get the common denominator. And say 20 minus 4x over x is bigger than or equal to 0. And then we're going to use the number line and say, okay, 0 is looking important and 5 is looking important. I got 0 and 5 by setting the top equal to 0, setting the bottom equal to 0. If I pick a number larger than 5, like 6, the top is negative, the bottom is positive, the whole thing's negative. Pick something between 0 and 5, like 1, The top is positive, the bottom is positive, we're good to go. Pick something negative like -1, the top is still positive, the bottom is still negative, so negative overall. I will point out that in this particular example, we would have been safe doing the quote unquote wrong thing or the less safe thing, but it doesn't always work. So I really want you to be clear on this. If you're solving inequalities, which we haven't really talked about in this class, but if you're solving inequalities, you typically don't want to multiply both sides by a variable because you have to think about how that could change the direction of the inequality. Okay, so here we don't want 0, we do want 5, so our domain is 0 to 5, like we said it should be, which means the range of the original function is 0 to 5, like we said it should be. Can't do that. Okay, so I know we've talked about this problem like maybe too long, but I really have to say there's a better way to do this than either of the ways we've done it, which I know feels kind of like, why would you show us the terrible ways first? Well, because these are the ways people are going to talk about it or think you're going to think about it in the future. So definitely graphing it's a good way to go sometimes. Doing this is kind of awful, but sometimes it's what people will expect. But here's what I would really say about this function. Just hiding the truth from you all. So I'm looking at the function 20 over x squared plus 4. And I'm trying to think about what the range is. And I don't want to graph it, and I don't want to find the inverse. So I'm just going to think about what happens as I plug in values of x. So if I start at x equals 0, if x equals 0, I get f of 0 equal to 5. So I can get a value of 5, for sure. And that's the biggest this function can ever be. Because if I pick any other value of x that's larger, or I should not even larger, but different than 0, although we have to be larger because our domain is saying x is bigger than or equal to 0. If I pick anything other than 0, that denominator is going to be bigger, which means that fraction is going to be smaller. So any other thing I pick for x, I'm going to get a smaller output. Now, I can get outputs as small as I want until I get down to 0. I can't get 0 because 20 divided by something is never going to equal 0. And I can't get a negative number because the top's always positive and the bottom's always positive. So I can think of, well, I can go as x gets larger and larger and larger, my function gets closer and closer to 0. So it looks like my range is, once again, 0 exclusive to 5 inclusive. That's kind of a way of talking it out to yourself. It's not super precise, but it is an idea you will use, especially in like 17C, 16, either B or C, when we talk about like the range of functions of multiple variables. So it is a good idea to kind of have in your bag. And when we get there, if you see me or Grant or anyone, we'll talk about this again. But so much of that. All right, let's look at this last one on the page before here. And we're probably going to talk about it all the ways again. So domain and range of this function. All right, well, let's talk about domain first. The domain, we need the insides to be not negative. So 9 minus x squared has better be bigger than or equal to 0. Definitely here, I would factor. So I'm going to factor this as, now be careful, it's not x minus 3 times x plus 3, it is 3 minus x times 3 plus x. Order does matter when you're factoring a difference of squares. So then on our number line, we get x equal to positive 3 and x equal to negative 3. And if I pick numbers like 4, 3 minus 4 is negative, 3 plus 4 is positive, the whole product is negative. Picking 0, 3 minus 0 is positive, 3 plus 0 is positive, the whole thing is positive. And picking negative 4, 3 minus negative 4 is positive, 3 plus negative 4 is negative, so the whole thing is negative. So I just want this. I do also want the endpoints because they make it equal to 0. So my domain is everything from negative 3 inclusive to positive 3 inclusive. Great. Domain usually not too terrible. The range, on the other hand, well, let's actually do it the way we just did the last one. So thinking about the range, one way to think about it is, I like to ask these questions. Basically, how low and how high can we go? And is there any kind of breaks in between those things? Well, if my domain is from -3 to 3, there aren't a lot of values of x. I mean, that's not true. There's an infinite number of values of x between -3 and 3. We don't really focus on all the infinity of them, but there are lots of choices, right? -3, -2.9, -2.8, -2.7, -2.666, right? You could go on and on and on and on. But we're not going to. We're going to say, well, like, okay, what could you plug in for x? And there's two answers to this question. What could you plug in for x that's in the domain that would make the y value as small as possible? What do you want me to plug in? I'll take anything. 3, that's one answer. Someone else, what's another possible answer I could plug in? Yeah, definitely, -3, totally right. Whether you plug in x equal to 3 or x equal to -3, we're going to get f of 3 equal to the square root of 9 minus 3 squared, and f of -3 equal to the same thing, square root of 9 minus -3 squared, which are both equal to 0. And that's the smallest this function can be, which makes sense, right? Because we've seen square root functions before, and we know that the smallest output they can ever give us is 0. Okay, now that's the lowest we can go. So that is how low we can go. Now, what do we want to plug in for x that's going to make this thing as big as possible? Well, let's think about this for a second. If we've got 9 minus x squared, whatever x is, you're going to be subtracting it off. And so if you want to make 9 minus x squared as large as possible, you have to make the thing you're subtracting off as small as possible. And what is the smallest that x squared can ever be? 0, right? It can't ever be any large or any more negative, right? The smallest x squared can never be 0. So to make this thing as large as possible, we're going to look when x is equal to 0. And we're going to get f of 0 equal to the square root of 9 minus 0 squared, which is the square root of 9, which is 3. And that is our high. And then we can get anything in between. If you wanted this to equal 2.7, you could find the value of x that would make it equal 2.7. It's kind of tedious, but I will just point it out since I picked a number like 2.7, fine. If you wanted this function to equal 2.7, we could certainly find an x value that makes that work, because I can square both sides. 2.7 squared, I don't know what that is. I'm not sure I actually do know what that is, but normally I wouldn't know what that is. It's 7.29. Is it? I think it is. Anyway, it's not that. Yeah, it is. Doesn't matter though. It's smaller than 9 is what matters. So then if I solve for x here, x squared equals 9 minus 2.7 squared, and x is equal to the square root of 9 minus 2.7 squared, which is definitely a number between -3 and 3. We're never going to actually do this, but I just want to point out that we found the low, we found the high, and any number in between the low and the high should be a number that we can get to. So our range here is everything from 0 to 3. So the low of 0 inclusive, a high of 3 also inclusive. We also could have graphed this one. This one is not that hard to graph. This function might not look super familiar to you. So let me do a couple things. I'm going to write it like this. I'm going to square both sides. X squared equals 9 minus y squared. I'm going to add y squared to both sides. So the x squared plus y squared equals 9. And now let me ask you, the graph of x squared plus y squared equals 9 is what kind of shape? Circle. But here, for f of x equals the square root of 9 minus x squared, it's just the top half of the circle, because the y values can't be negative, the square roots only give you positive results. So we get the top half of the circle of radius 3. Which, okay, 3, sure. Which I think looking at, you can totally see that, oh yeah, the domain is everything from -3 to 3, and the range is as low as 0 and as high as positive 3. Oh, we can't see, I'm sorry. Thanks. Yeah. So let me say that again. Looking at the circle, the domain is everything from -3 to 3, and the range is everything from a low of 0 to a high of positive 3. And you could also do this one where you actually found the inverse function kind of thing. But again, it's kind of a terrible thing to do, because here, this function, as you can kind of see, if you invert it, it's not a function when you find the inverse. So doing it that way is less than ideal. And we could do it, but we've only got a minute left, so I probably shouldn't try to just jam it in there. That's not really the way you want to do it. So, big picture for range, you can find the range in a lot of different ways. You can find it by graphing the function and seeing what the y values are. You can find it by finding the inverse of the function, finding the domain of the inverse, or you can do this kind of hand wavy thing we did at the end, where you say, well, how big can the function be? How small can the function be? And try and get a good idea that way. There definitely is a question on the homework like this second to last one we did here, the 20 over x plus 4. So just be aware there is something like this on your homework assignment, I think. I'll double check just to be sure. Something else. Oh no, that's another. All right. I will not see you all on Friday. Have a lovely 3-day weekend. I'll see you all on Monday. No quiz. I'll be over and dropping, or not dropping, C class.
Going to like the 17 or 16 series.